So in this part of the chapter, we will talk about free fall. What is free fall? It's common experience that all objects, if they are dropped from a height or if they are dropped from a table, they do fall towards the earth. Earth has a special thing called gravity that pulls all objects towards its center. The acceleration of the object towards the earth is always a constant with a magnitude 9.8 meters per second square, whether the object is moving up, down, or is at rest. The acceleration due to gravity is independent of the speed of the object, and it always acts on all objects equally. Gravity and acceleration. The rate at which the objects accelerate towards the earth is 9.8 meters per second. This acceleration is same for all objects regardless of their mass. In other words, falling objects accelerate at a constant rate of 9.8 meters per second. Note, the ball or whatever object you are dropping isn't traveling at 9.8 meters per second, it is accelerating at 9.8 meters per second. So ball's velocity will always continuously increase, but it will always increase at the same acceleration of 9.8 meters per second. So look at this picture. If you drop a ball from a height, say any height, this means that its initial velocity is 0 meters per second and it is pointing downwards. In the first second, it will travel 4.9 meters. In the second second, it will travel 14.7 meters per second. In the third second, it will travel 24.5 meters per second. However, its velocity is affected by a constant acceleration, which is given by the value of g, which is acceleration due to gravity. Now here's something I want you to think about. A person standing at the edge of the cliff throws one ball straight up and the other ball straight down at the same initial speed. Ignoring air resistance, the ball to hit the ground below the cliff with greater speed is the one initially thrown upwards, downwards, or neither. Think about it for a second. In one case, the person is throwing the ball downwards, and in the other case, he's throwing the ball upwards and then the ball is falling down from the same height. Think about what we're actually doing here. The answer is neither. Both will hit the ground at the same speed. But the question is why? Well, in order to understand this, let's look at this picture. If you throw the ball up with certain initial velocity, say 20 meters per second, what is going to happen is acceleration due to gravity will start attracting it downwards towards itself, and the speed on its way up will decrease until at the top of its flight, the velocity goes to 0. Now on the way down, velocity will start increasing until it reaches back to the point where the hand was, at which point the velocity going up and velocity coming down will be exactly the same. So it doesn't matter if you were to throw the ball up or down, when it reaches the same level in its motion, the velocities will be exactly equal. Now let's look at a problem. You throw a ball into the air with speed 15 meters per second. How high does the ball rise? In this case, we will use the same equation of motions that we have been talking about before. However, the acceleration will always be 9.8 meters per second. So if a ball is thrown upwards into the air, it will reach a certain height and it inevitably will always return back to the ground. Okay, so if your initial velocity is 15 meters per second, there is one thing that we can absolutely for certainly say about the velocity at the top. The velocity at the top is always and forever equals to 0 meters per second. Note that the acceleration due to gravity that's attracting it will have an equal magnitude, here and on its way down. Right? However, the velocity at the topmost point will be equals to 0. So now the question is asking, how high does the ball rise? So we are looking for delta x. Some people want to call it delta y because now we are talking about the coordinate system, but it really doesn't matter. It's just a symbol. Okay? So in this case, what can we do? What equation of motion should we use? Well, let's try the first one, okay? So that one is VF equals V naught minus GT. Now, note it's this first equation of motion. Now, why do I have a minus sign here? The reason why I have a minus sign here is because G is always pointing towards the center of the earth, okay? My second equation, well, that one has a T in it. Is the question giving me a T? No. Well, that might be a harder equation to use. Okay? So number 2. What was that one? That was delta x equals V naught T minus half GT squared. The direction of G downwards again, that's why I get a minus sign. Okay, this one also has a T in it, so maybe not the best one to use. So now let's look at the third one. This is 2G delta x equals VF squared minus V naught squared. Okay, what about this one? It has a G in it, it has a delta x in it, it has a VF and a V naught. Well, that might be the equation that you want to use here. So let's plug in the numbers, right? So now that I know I'm going to use equation number 3, what do I have? 2 minus 9.8 meters per second squared times delta x, this is what I'm looking for, equals, I know for certainty this is equals to 0, because at the top it can't have any other values except for 0, minus V naught squared, which is 15 meters per second squared. Now that I have everything that I need to know in this equation except for delta x, I can do a little bit of algebra and come up with an answer for delta x. Go ahead, come up with an answer for delta x. Another really good example. A penny is dropped from the observation deck of the Empire State Building 369 meters above the ground. With what velocity does it strike the ground, and how long does it take the penny to strike the ground? So like all other problems, we will start by drawing a picture, right? So let's draw a building, right? Ooh, my building is not that great, but it's okay. And there's a penny, and it is being dropped, okay? What do I know? The penny is being dropped from the surface, right? And the height of the building, it is 369 meters, okay? And I know that since it is being dropped, the word dropped means that its initial velocity is 0 meters per second at the top, okay? It's asking me what velocity does it strike the ground, so it's looking for VF, and it's asking me how long does it take for the penny to strike the ground. So delta T equals what? Okay, I know for a fact that, so delta X is this one, G is 9.8 meters per second, because it is per second squared, because it is a free fall, okay? So what can I use in these expressions? So I'll just write number 1 here. And which one should I be using in order to calculate any one of them? So let's do the delta T first. What do I know? Do I know VF? No. Do I know V naught? Yes. Do I know G? Yes. Same thing here. I know V naught, I know delta X, I know G, and I can calculate for T. Okay, so let's look at equation number 2. In order to solve for my T, if I use number 2, what do I have? Delta X equals V naught T minus a half GT squared. V naught is 0, delta X is 369 meters equals minus a half G, which is 9.8 meters per second, and T squared. Note, since I am moving down, I'm going to put a minus sign here, okay? This minus sign and this minus sign gets canceled, and I am left with 369 times 2 divided by 9.8. A little bit of algebra, plugging numbers in, will help me solve for delta t. Okay? Part A. How do I calculate VF in this case? Okay, let's look at equation number 1. Equation number 1 says VF equals V naught minus GT. Okay? I know V naught equals 0. That means VF should equals minus GT. I just calculated T from that expression, and I can plug that value in here, 9.8 times delta T, whatever this was here, plug it into here, solve it, come up with an answer in meters per second. So now do a quick calculation. Note that I am not doing this for you.